Welcome to Firefighter Safety and Survival, Chapter 16, Engineering Safety into Equipment. This chapter discusses the importance of engineering safety into apparatus and equipment, the safety curve and phases of improvement, groups that influence safe design, the use of research, education, practice, and policy in incorporating safety into design, and retrofitting safety. The objectives we're going to cover in this chapter are as follows. We will discuss why safety should be a primary consideration in the design of apparatus and equipment. We will list some of the groups responsible for ongoing or originating safety. We will describe how manufacturers can improve safety, thus better serving the fire service. We will also discuss the advantages of creating a fire-based safety invention clearinghouse. Compare the level of safety when designed into equipment versus safety that is retrofit into it, and explain how a cost-benefit analysis can justify investing in safety techniques. Safety is an evolution. Did you ever notice how some equipment becomes safer with each newer and subsequent version? You've probably noticed that on automobiles or things that you consume every 2 to 3 years in your home. One example of safety being an evolution are highway guardrails. Significant research, testing, and design changes have allowed them to improve safety on the road. There have been many design changes to guardrails because of poor performance. The advantage of this change model is that trial and error eventually can improve safety, but the downside is that once a reasonable amount of success is attained, the design changes tend to cease. Once there is a perception of safe enough, attention tends to be diverted to another problem. Electric motors, hydroelectric dam turbines, and even fire pumps use efficiency and power charts to demonstrate what output can be predicted based on input. The standard representation is an XY graph with a horizontal and vertical axis that each represents different data. The horizontal plane, which is X, can represent effort or power, which is input, and the vertical plane, Y, represents gain in efficiency or output. Eventually, the line levels off at a point where further increases in energy produce little improvement. We can use a similar chart to graph different types of improvements. For example, ranking skills for your daughter's t-ball team. Just one random example. Let's discuss the safety curve. Improvement phase 1. If you want to increase the level of safety at your training academy, you might rank the factors involved. The first of the progressive phases with the best chance for improvement might be wearing sufficient personal protective equipment or PPE for the task involved and maintaining an attentive behavior. Rather than teaching what the PPE can do, you emphasize what it cannot do. That lecture is expanded upon by concentrating on what it cannot do if it is used improperly. You demonstrate the different levels that are required for specific tasks. Improvement phase 2. Your best chance of success is to continue building off of what worked in improvement phase 1. The Fire Academy is ready for another level of safety training, so you decide to use the teamwork approach to teach solidarity and empowerment. You break the class into companies with specific goals and rewards for success. The class learns that on an emergency scene, or at an emergency scene, there is no quote-unquote franchise player, and that success is gauged on the group's accomplishments. They learn to check each other's gear before entering a dangerous area and watch each other's backs. They practice using communication and empowerment with the challenge and response model of crew resource management, CRM, and are constantly forced to adapt and overcome obstacles. Failures are evaluated and successes are rewarded. Although we may not see drastic improvements in the second step, the skills they are learning are setting them up for success in the future. The safety curve has made its arc and is starting to level out. Building construction, chemical hazards, new technology, and public expectations are all dynamic influences on our safety. If we remain static, our skills will slip and the competitors will overtake us. Improvement Phase 3. Once a firefighter completes basic training, the learning cannot stop. It's important that continuing education is treated as more than just time, actually improving the skills and knowledge of those who attend. Initiative 16 calls for continued improvements to safe design and safety as a primary consideration when purchasing equipment. Rules, regulations, standards, and liability all work to ensure that safety improves until it levels out. This is where vigilance on our part can step in and continue to push to make it even safer. The first step is to look at those who need to be encouraged to keep improving. When it comes to safe equipment, procedures, and apparatus, the push for a safer design can and must come from several different directions. The primary reason is because each can be successful in its own way. For example, Initiative 6. Designing safety into new and existing equipment needs to be somewhat of a team sport. Working together can also increase the awareness of the improvements themselves. Near-miss reporting can benefit the fire service. A comprehensive plan must include ways to disseminate the information. Initiative 16 could be better supported with the institution of a Safe Design Award Program. Categories of awards could include those who influence safe design, including National Fire Protection Association NFPA committees, research institutions, government agencies, manufacturers, and individual firefighters. Let's talk about NFPA committees for a moment. The NFPA has led the way for standards that are used by fire departments everywhere, and not just in the United States. Many of these standards have been adopted around the world. According to the NFPA, technical committees are the, quote, consensus body responsible for the development and revision of an NFPA document, end quote. They are composed of manufacturers and users and other interested parties and review existing standards and support revisions every 5 years. The three major categories of NFPA standards directly affecting operations of the fire service include A. Equipment standards, B. Apparatus standards, and C. Personnel standards. With regard to equipment standards, one of the most familiar accomplishments for NFPA when it comes to increasing safety is through the use of equipment standards. Common portable equipment such as the self-contained breathing apparatus, SCBA, and thermal imagers has been researched and tested in an effort to ensure their safety. It is also common for some equipment to be compatible with similar equipment from other manufacturers. Sometimes it's not just the equipment, but how it's used in conjunction with other similar equipment. PPE components are often tested individually. One example is a structural firefighting boot. As stated in a newsletter released by the Fire Service selection of the NFPA, quote, PPE items must be worn together and therefore evaluated together, end quote. It makes common sense. As a result, the National Institute for Occupational Safety and Health, NIOSH, initiated a research project to review ways of conducting quote-unquote leakage tests by combining various components of PPE that are normally worn together. In regards to personnel standards, like equipment and apparatus standards, personnel standards change as well. In 2009, a new standard was developed to assist in the application of the National Incident Management System, NIMS, NFPA Standard 1026, which is the standard for incident management personnel professional qualifications, which describes the job performance requirements of each position in the command system. Without standards for personnel, it is likely that some duties might be overlooked at a complex incident or that different positions would overlap. Let's talk about research institutions. Research institutions that are the most involved with firefighting are government-based and educational institutions. Some examples are the National Institute of Standards and Technology, NIST, and Worcester Polytechnic Institute, or WPI. Many times, the fire service makes decisions based on what we have been taught or what feels right. Research institutions, on the other hand, prove or disprove what we thought we knew. Although they operate from outside the fire service, their studies contribute greatly to firefighter safety. Like equipment and apparatus standards, personnel standards change as well. In 2009, a new standard was developed to assist in the application of the National Incident Management System, or NIMS, and NFPA 1026, the Standard for Incident Management Personnel Professional Qualifications, which describes the job performance requirements of each position in the command system. Without standards for personnel, it is likely that some duties might be overlooked at a complex incident or that different positions would needlessly overlap. Scientific methodologies prove or disprove concepts about things we use every day, like positive pressure ventilation. Governmental regulations and standards we're going to touch on right now. Many times, safety designs are adopted from automobiles and are configured for emergency apparatus. Some examples are anti-lock braking system, ABS, supplemental restraint system, SRS, and rollover protection. The U.S. Department of Transportation, DOT, will periodically issue safety requirements to trucks that carry over to fire apparatus or other aspects of our job. Industry has also been a significant factor in bringing safe design to customers or consumers. Outside the fire service, Cirrus Aircraft was the first manufacturer to provide an airplane parachute standard on all models. Although many safety standards are required through regulatory agencies, sometimes manufacturers such as Cirrus Aircraft are responsible for significant design changes for safety. Some of our equipment has rounded out at the top of the safety curve and has been ignored for quite some time as a result, unfortunately. One example are aluminum ground ladders, and they haven't changed much since 1942. One way that manufacturers could assist fire departments in improving safety is to identify how they involve safety in their design process. Departments that purchase equipment could be provided with information from the manufacturer about common injuries associated with similar equipment and what they have done to reduce the risk of injury with theirs. Many already supply training and safety information on a CD or a DVD. These manuals could weave safety messages throughout instead of having them all in front. The benefit to the firefighter is an improved cognizance of safety during design and production, and the advantage for the manufacturer would be to reduce injuries with their model. Not all equipment needs to follow the industry's or NFPA's lead for safety standards. A large portion of equipment and techniques used on the fireground today were adopted and adapted, or created and perfected by the people using them. Both portable and mobile equipment have been invented or improved to make a job easier or safer. Portable equipment includes countless tools that have been invented by firefighters, but one of the best examples is the Halligan tool, which became the industry standard for forcible entry. Now, even 70 years later, the fire service has been unable to improve much over the original design. The fire service could benefit from a clearinghouse for inventions or suggestions to improve safety. The main advantage would be that safety could be evaluated and designed into new inventions. Properly trained and interested individuals could be assembled into a committee, review the equipment or technique, compile concerns, and submit it for testing. If a firefighter invented an ingenious piece of equipment that had financial incentives, it could be easily submitted to fire manufacturers involved with the committee. Occasionally, members of fire departments join forces to invent their next apparatus. One complaint about a water tender with a front-mounted pump was that it was difficult to unload with two people, so the firefighters worked on a rear-mounted design. They chose an apparatus manufacturer that accommodated their design. Although none agreed to build the bracket, the firefighters found a fabricating shop to build it for them. When the truck was completed and the bracket system installed, training ensured that one person could unload the portable tank and supply water from a draft in less than 3 minutes. The downside was that it was never officially tested or certified. The fire service has no mechanism for introducing new designs for testing, improvements, and acceptance. One of the most effective ways to incorporate safety is during the initial design process. Other organizations have understood the benefits of built-in protection, including NIOSH, when they established a program called Prevention Through Design, or PTD. By reviewing injury data, all new equipment and techniques can be engineered to prevent future injuries. The process involves 4 functional areas of stakeholder input: research, education, practice, and policy. PTD sometimes works with research organizations to establish the injury prevention needs of industry and design equipment better. When researching injuries, they can be categorized as either specific, acute injuries, or repetitive motion, or chronic injuries. Specific injuries. These are acute injuries that are produced when a specific event causes an immediate injury, such as a burn, a fractured leg, or a laceration. Several possible contributing factors to specific injuries include proper equipment, proper positioning, proper technique, design considerations. Repetitive motion injuries, on the other hand, are cumulative in nature. North Carolina State University found, or North Carolina State, or NC State, you've probably heard it referred to. North Carolina State University, or NC State, found that numerous repetition injuries were occurring in the construction industry as a result of continuous nail gun use. As a result, NC State researchers developed a prototype that the workers found more comfortable to use. As far as firefighters are concerned, exposure to sirens, patient lifting, and pulling a ceiling during an overhaul can all lead to chronic injury because these are activities that occur over time, perpetually. There are several risk factors to an activity that can lead to a repetitive motion injury, including forceful exertion, awkward position, duration, compression, vibration, and poor physical health in general. The next step in PTD is education. The Alaskan fishing industry is one of the most dangerous professions in the country, so to reduce fatalities, the U.S. Coast Guard reviewed data on fatalities. In a report issued in 2010 regarding fishing industry risk factors and recommendations, NIOSH identified many ways to reduce deaths, as well as the success of implementing the recommendations. These recommendations were more inspections, education of the crews, and those recommendations led to a 60% reduction in the fatality rate to crab fisheries in the Bering Sea. That's significant. It is one of the most dangerous professions in the world. Firefighter injury data shows that a significant cause of injuries is slips and falls. Similarly, the Navy noticed a significant portion of lost time injuries was in their firefighting divisions. As a result, the Firefighter Injury Prevention Training, or FIPT project, was initiated. The FIPT concentrated its efforts on education, creating videos that display proper footing techniques, etc. Let's discuss the concept of designing safety. Once research has shown a way to reduce injuries and workers are educated, the next step is to put it into practice. Taking design safety to the next level is Safer Design, a nonprofit organization with a goal of, quote-unquote, designing out hazards through states of construction and the entire life cycle of a building. Through research at the University of West England, the Safety Targeted Assessment via Gateway Evaluation, or STAGE, was created. Two examples of ways to increase the safe design of a building include the worksite layout and future planning. With respect to the worksite layout, some considerations of worksite layout include hazard identification, plot plans, site preparation, and building practices. With future planning, the safe design of the building also takes into consideration maintenance and future use of the building and grounds. Even window washing and other normal maintenance duties can be planned for to help eliminate falls. The last step is to make it policy. Many organizations have a safety policy, but an effective policy includes all levels of employees and uses safety as a primary consideration with all decisions. One of the best policies that should be standard is purchasing and equipment apparatus alteration guidelines. A checklist could provide guidance to ensure that safety is a primary consideration and is thoroughly evaluated at the time of purchase. Initiative 16 urges emergency response organizations to incorporate safe design even when it is not required. History is full of examples of tragedies that could have been avoided by providing safety equipment that was suggested but not necessarily required. After two Canadian National or CN Railway freight trains collided head-on in Anding, Mississippi in July 2005, recommendations from the National Transportation Safety Board, NTSB, to the Federal Railroad Administration, FRA, included mandatory installation of specific safety equipment. The report also shows that positive train controls, or PTCs, have been strongly recommended by the NTSB since 1990, and that the FRA did not have a system in place to control runaway trains when the operator failed to react. A cheaper substitute could have been installed. Alerters have been available for retrofits on locomotives, which monitor signal controls as the train passes them. We need to investigate how we can retrofit safety into all of our existing equipment. CN Railway's decision not to retrofit its fleet voluntarily, or even an emergency response organization's decision not to supply all personnel with a new piece of safety equipment, could be a result of cost, availability, and perceived need. Let's examine cost. The primary reason for not complying with any voluntary safety standard is many times directly related to its cost. Anytime voluntary safety costs money, it is weighed as a, quote, potential return on investment, end quote. I'm certain you've all heard that phrase before. Weighing costs against risks happens in the fire service as well. For example, suppose you read about several failures of fire stream appliances such as gated Ys, Siamese fittings, and manifolds around the country with injuries reported, and your fire department uses similar models. Some ways you can help determine your options related to cost include research, phasing in, grants, and in terms of research, the first step is to evaluate your concern versus the cost, and that will help you complete thorough research. Sometimes you need to determine if your current equipment puts your personnel at risk. Then you need to look at severity, probability, and exposure, or SPE formula. The mathematical formula also proves that if we reduce one of the factors to zero, there is no risk at all. Therefore, eliminating the use of appliances whenever possible makes it a non-issue. A new approach to safe design by manufacturers might start to include pressure relief valves standard on all appliances. With phasing in for every unsafe piece of equipment that is replaced or improved, the chance of an injury or death is reduced. It could be that most active companies get the new equipment, or that the equipment is added when another component is replaced, such as fire hose. Then there are grants. Initiative 10 puts an emphasis on the awarding of grants based on their intent to improve safety. It is important when specifying the new appliances that research has been done to ensure that the new equipment is substantially better than the pieces being replaced. Firefighters and other emergency medical services or EMS providers are continually at risk for back injuries due to lifting heavy patients. Some grants intended for safety are a perfect match for equipment used to complete the job in a safer fashion. Some examples are grants for lifting and dragging mats, mechanical advantage equipment, and power-operated cots. Now we'll discuss retrofitting safety. Another consideration for not complying voluntarily is not having the appropriate equipment readily available. Voluntary compliance is much more attainable when it is easy. When it comes to retrofitting fire apparatus, there are several examples of equipment that might not be easy to purchase. For example, retrofitting seatbelt warning lights on a 1986 pumper. And then look at need. The final reason voluntary compliance can suffer is that the added level of protection is not viewed as a genuine need. One great example is if citizens and builders were convinced of a need for residential sprinkler systems, it is likely many residences would be equipped. If the problem is not conveyed, safer equipment will never prevail. Let's draw some conclusions. First, Initiative 16 encourages safety as a primary concern when ordering apparatus and new equipment. Most of us put more weight on cost, aesthetics, and even opinions. New improvements to safety can come from several different sources, and each must be encouraged to participate in the evolution. Manufacturers should become more active in firefighter safety and make it easier for firefighters and their departments to get new ideas tested and developed. The key is to ensure that we never give up on a better design. Although safe design is better achieved in the planning stages of new equipment and apparatus, a plan to retrofit safety is just as much a part of the process. Ignoring the fact that safety can be improved with our existing equipment and apparatus would be a mistake. So let's summarize what we covered in this chapter. Many engineers use a safety curve to predict an output based on specific input. The standard graph representation shows a rapid increase in output, but a gradual leveling off over time and energy. The same graph can demonstrate how safety improvements increase and taper off when they are deemed safe enough. This safety curve can be broken down into different phases of improvement. Phase 1 is rapid growth in the safety improvements. Phase 2 begins to slow the climb, and additional efforts are likely to yield fewer results. The final portion, Phase 3, tends to taper off with few noticeable results. We also talked about how improvements to the design of safety can originate from several sources, including NFPA committees, research institutions, governmental regulations and standards, and manufacturers as well as firefighters. We covered how the NFPA creates individual standards for equipment, apparatus, and personnel. NIOSH developed a program called Prevention Through Design, consisting of research, education, practice, and policy. NIOSH research classifies injuries as either specific, which are acute, or repetitive, which are chronic. Specific injuries can be attributed to equipment positioning or technique. We discussed how repetitive motion injuries are commonly caused by forceful exertion, awkward positioning, duration, compression, vibration, and poor physical health to begin with. Once workers are educated, practice is the next step. This can be accomplished by worksite layout and future planning. Some considerations of worksite layout include hazard identification, plot plans, site preparation, and building practices. And we also, and finally, talked about how safety can also be retrofit to existing equipment, but is subject to cost, availability, and need. Okay, class, that concludes chapter 16. Thank you for your entire semester's worth of attention. We hope that this tool has been a good supplement to your study of the text itself. And remember, this is meant to supplement study for the text. So don't give up on that concept here in the last chapter. Make sure you study your text and use this as a support to that. As with every other chapter, if there's anything that's unclear in this chapter, please make sure that you contact your instructor. And again, thank you for your time for this entire semester. Take care, and we'll see you in a future class.